Hello everyone, and let us talk today about regulator design. So, regulator design problem is the fundamental problem in theory of system science. And we will start by inspecting the classical controlled system representation where we have a plant of interest that is driven by the regulator or controller. So here I will put controller, and which supplies the input to some generalized plant. And there is a feedback signal, of course, as a measurement from the plant that is sent to be compared against some reference point or reference signal, such that the error is generated and fed it into controller and regulator. In other words, this output of the plant is fed back, compared here, and then controller provides the input into the plant. We also can think about possibility to add disturbances. But in general, this is the structure of the controlled system that we understand that this system is the feedback control system, and the main question in the regulator design is the closed loop system stable? So is the closed loop system stable? It's a very simple question, but it's fundamental one, because the answer to this question depends on the controller design. In other words, the controller design has to ensure that the affirmative answer to this question. And therefore, if we consider just some generalized plant, so here I'm saying think about of the plant dynamics as being some linear system where xp is a state of the plant, ap is a state transition matrix associated with the plant, xp of t plus bp u of plant t, and y plant of t is equal as cpx plant of t. By providing these equations, in other words, A plant, B plant matrices, and C plant, we completely determine the plant model dynamics. So one can say in the input-output representation that this will take the following form. Y plant hits the plant and output of the plant is YP. So this is exactly what we get with the following description of this plant. And if we look at this, what about controller? Controller is also a dynamical system. So controller, it's a dynamical system of the similar structure. It's just, we call XC dot, so it's the state of the controller, AC XC plus BC U of C, and here we have a Y of controller, Y of CT is equal CC XC plus DC UC. Okay. In other words, controller is completely defined by the matrices AC, BC, CC, and DC. In other words, if we look in the input-output system representation, our controller has as input UC, and the output is Y of C. And one can now interconnect plant in the controller, and it can structure the interconnection between a plant and controller in the same way as it is done here in this classical formulation that I'm going to denote here. In other words, let's think of the following. So let's say that Y of C output out of the controller is going into the input of the plant. In other words, we just connect these two systems, and another one that input into the controller is output of the plant augmenting just for some signal V of t. So taking these two equations, we have the following. So here is the plus, here is the V plus, and that is U of C. In other words, one can easily see that this representation is similar like this one. How? Just look how I can rewrite this. Think about that this is V again, plus here I'm saying that U of C is V plus Y plant, controller, Y of controller is U of plant, we have a plant, and output of the plant is something that is here sent back to the system. So as you can see, these two configurations are almost identical. Therefore, this interconnectivity that has been established by linking the controller and the plant combines these two dynamics, and easily we can write the following representation of the controller dynamics as X of C equal AC X of C plus BC U of C, which is now Y plant plus V, and which finally becomes AC X of C plus BC. Y of plant is here CPX plant, so BC CP XP plus BCV. And on the other hand, we have here that the same way X plant dot is going to be AP XP plus BPYC equal, and once we apply all substitutions, XP plus BP, YC is UP which is BPCC XC plus BPDC UC, and finally this leads to the expression AP plus BPDCP XP plus BPCCXC, and we have plus BPDCV. Okay, such that combined dynamics of the controller state and plant state can be written nicely in the state space form as follows. Just think about that this is now interconnected 2x2 system with the states of the controller and with the states of the plant, where AP plus BPDCCP, it's 1 entry. Here this is BCCP. 2 entries BPCC, and this is just AC term here. Here is just X, P, X, C, and there is this external input that drives both states, B, P, D, C, multiply V, and here we have a B, C. What about output? Output is also Y of t is equal Cp 0 and then X of P, X of C plus, here I'll put a 0 V, which denotes that direct transfer from V into the output is 0. In other words, in this way we can identify the three matrices which describe the interconnected closed loop system dynamics. So this is ACL, BCL, and CCL. Okay. And now, as we return to our initial question, is the closed loop system stable? Is intrinsically associated with the stability of the ACL, because ACL stability is directly linked by the entries of the ACL matrix with a plant through the AP, BP, DP, and CP, and it's also associated with the structure of the AC that is coming from the controller. In other words, what we see is that X dot equal ACL X, assuming that V equal is 0, has a solution as X of t e to the ACL t x 0, and therefore stability of this system is determined by the eigenvalues of the ACL. In other words, we have to think about control design problem as following problem: how to design AC, BC, CC and DC such that the closed loop system is stable. Also, we see that we have two important things that we can change in the controller. First is the controller order, NC. So order of the system, controller, and second one, entries into AC, BC, CC and DC. Essentially, parameters which are within the matrix AC, BC, CC and DC can be changed also as another degree of freedom. Interestingly enough, there is a following representation that one can easily recognize, that ACL matrix given here can be written as follows: A plant 0, 0, 0 plus B plant 0, 0 identity. Here will be DC, CC, BC, and here will be AC, which all multiplies CP 0, 0 identity. What we see from the following is that ACL, if this is some A hat plus B hat plus gain C hat, and this is the K matrix of the gain, is the matrix ACL is a matrix that has a certain eigenspectrum structure that can be perturbed by this gain K. In other words, find the K gain K such that ACL is stable. This is very nice for understanding of synthesis of the regulator or controller design, which states how to choose this K gain matrix with a given plant AP, BP and CP, and therefore the controller order such that the closed loop system is stable. We recognize that controller design has two parameters again that I want to emphasize. First is the controller order, and again the gain value, the entries of these AC, BC, DC and CC, which can ensure the closed loop system stability. In the next lecture, we are going to describe how systematically we can design controller, exploring these two degrees of freedom.